Welcome everyone statewide in the state of North Carolina to our webinar today. So I'd like to introduce Sean Bragg. Sean is a former military electrician. That's where he got started in the U.S. Coast Guard. And after leaving the Coast Guard, he had many roles in lighting. One of those is actually spending time as a field service engineer for Lutron Electronics, and then also as a BMS technician for Hoffman Building Technologies, and then as well as inside project manager for a lighting rep agency. So right there, those three that we just mentioned, there's a wide variety of lighting control experience. So I'd like to invite Catherine now to finish us out on the introduction.
Okay, so Sean started the Paratus Service Group in 2013 to serve as a locally based commercial lighting control service provider. Since then, Paratus has grown to employ multiple field engineers and sales representatives across the eastern half of the United States, providing lighting control services, including consultation, design, sales, commissioning, and training. I'll hand over the presentation to Sean, who will review today's agenda topics.
All right, thank you, Catherine and Bob. I appreciate it. I appreciate everybody joining us and taking time. I'm going to go ahead and share my screen here. So hopefully everybody can see the presentation. That number there is my cell phone number, so feel free to jot that down. I know this will be recorded. My email address is there as well. You're welcome to reach out at any time with any questions, anything we can help you with. And we'd be more than happy to. All right, so I'll back up one. I'll just going over my background again. I am a field engineer by trade. I've got a lot of hands-on experience with lighting control. I'm not an electrical engineer. I'm not a designer. My experience is all very practical, very hands-on, real world. So while we're going to talk a lot about some technical things, we're going to hopefully walk a line between kind of technical stuff that you can use and some hands-on, along with hopefully some stuff that is a little more general and summarizes everything. All right, learning objectives. Understand why lighting control is essential for today's buildings, commercial spaces, and office environments. Compare the load types, control solutions, and technologies, including some pros and cons of each one. And we're going to look forward to some new technologies taking hold in today's lighting control and building management applications. Here's the agenda broken down in a little more detail. We're going to talk about some features and benefits of lighting control, along with some challenges and opportunities that we face in the controls world. We're going to talk about some load types in the lighting world, go over wireless, and then we're going to talk about color tuning, CCT, circadian lighting, and then hopefully have some time for some summary and questions at the end. So why do we need lighting control? Why are we all here, right? Well, we start with just standard on-off, the light switch, the good old light switch, but automating that, getting off and on. Well, there's some really important reasons that we do that. First and foremost, obviously energy savings. Turning lights off is the simplest way to save energy. We all know that from back in the day when your parents would tell you to turn the lights off when you left the room. Safety, this isn't just safety in terms of having light. It's important for us to remember that lighting, while we think about a lot of the advanced things that lighting can do, and we're going to talk about a lot of the advanced things lighting can do, at the end of the day, lighting is a life safety component. Ensuring the lights are on when we need them on is extremely important. It's easy to forget in our world, but that safety component is really the job number one. And then standardization, ease of use. How easy can we make it for our staff and for our team members to use the lighting? On top of on-off, we add dimming. So dimming opens up a whole new world of lighting control. So we can enhance that lighting savings through dimming. We can also improve mood and aesthetics and improve productivity. So an analogy we often use is a car. A car that just goes 100 miles an hour and goes 0 is not worth very much. Likewise, a light that just goes on and off, there's a whole world in there that we're missing. Mood and aesthetics. we pay lighting designers and interior designers a lot of money to really, excuse me, to really set the mood in a space. But getting the lighting right can really enhance that and take it to another level. And productivity, getting the lighting right, excuse me. Getting the lighting right in a space can really help people be more productive and make the spaces really to be able to use their full potential. So why now? Well, there's a lot of reasons why now. First, there's a big focus on sustainability. Energy efficiency is attainable using LEDs, using controls. So we have the ability, we have the technology right now to be sustainable, to use sustainability. And the LED technology we have is available. It used to be that fluorescents were the standard and LEDs were a nice kind of, were a nice to have option or a luxury item. But that's no longer the case. LEDs are readily available, can be used in every application, and that energy efficiency is attainable. We can take advantage of the technology we have currently. LED is basically a computer chip installed throughout your building space. So using LED allows the infrastructure of the building to kind of serve as the backbone of a much more advanced technology system. We can use sensor arrays and other things to really include sustainability and smart technology throughout the building. And then even if you don't want to do it, code is such that you're going to have to do it. Two leaders in this space, California and New York, are implementing local laws and Title 24 that require energy and building technology and sustainability. So even if you're not convinced by what we talk about today, you're going to have to be forced to do this kind of thing through law and through code. So understanding this and being able to use it is going to be essential. And it sounds like somebody's microphone got turned on. There we go. So there are some challenges with control, challenges that we're going to need to focus on. I mentioned in the previous slide that fluorescents have even just 10 years ago, it's crazy in how fast-paced this has been, that fluorescents, even just 10 years ago, were the standard. Well, LEDs are now the standard. And that shift over such a short period of time means that there's a lot of figuring things out on the fly that we're having to do. So compatibility has become an issue, ensuring that drivers and LEDs work together cleanly and clearly. That can be challenging, especially as all the manufacturers are trying to figure out what the standard is going to be moving forward. Complexity in installation. As we've said, this has been a pretty big shift, the fluorescent to LED shift recently. So installers needing to understand how to install these systems, there's a lot of learning that has to be done in a pretty short amount of time. So understanding the specific requirements of different installation types, it takes some time, and there's definitely complexity. Exaggerated claims, total cost, these are all important things to know. So let's talk about LEDs. There's a lot of different types of LED fixtures out there. There's traditional ones, there's more unique. One way to think about it is in terms of the way that fluorescents used to work. A lot of people understand that. You've got the ballast, you've got the tube. Well, the analog to that in the LED world is the driver and the LED engine or the LED array. So each one has two very specific jobs, the LED driver and the LED array, but they work together. So an LED driver is analogous to what we used to use fluorescent ballast. The LED driver is going to determine the load type of the fixture. It's going to determine the input voltage. There are different types of drivers. We're not going to get into constant current, constant voltage. We're not really going to dive into that. What's important, though, is that the driver matches the engine. The engine, the LED engine, that's the actual LEDs themselves. That's going to determine your beam spread, your color temperature, your lumen output. The good news is the fixture manufacturers are pairing these together. The fixture, the designer doesn't typically have to pick a driver that's going to match the LED engine. That's something that's going to happen in the manufacturer's level. But it's important to understand those two components, especially again, because when you're looking at that spec sheet, a lot of those options are built into that. The load type, the lumen output, the color temperature, those are all really important things to understand, and those two things are going to factor together in the LED. Dimming expectations. So for those of us who've been doing this for a little while, we're all a little spoiled because we all kind of experienced lighting control first through the incandescent light bulb. And the incandescent light bulb really, really spoiled all of us. Incandescents dim beautifully. Their color is gorgeous. The color shifts a little as it dims, it gets warmer. They've got a really, really good low level, high CRI, and we're all kind of trained to use that as our baseline. And that's a really difficult level for other types of lighting to achieve. So this graph here shows the difference between perceived light and measured light. And this is one of the really big challenges we've run into. So measured light, the amount of light we actually see using a meter compared to perceived light. Well, as you all know, the human eye adjusts. If you're in a dark room, your eye opens up, you let more light in, it changes the perceived light level of that space. So the challenge we run into is if we've got a bulb or something that's rated at 1%, well, that 1% is going to be measured. But the human eye might not see that as 1% light level. So this graph kind of shows you that difference. Up high in that higher range, it's not a big deal. You can see that the line is mostly at a 45-degree angle, close to a 45-degree angle, and big chunks of dimming account for big light level changes and big energy level changes. So if you're in an area where we're just looking for energy savings, low light level isn't all that important, LEDs are going to perform fine in that regard. We start running into an issue, however, on the lower end here, because on the lower end, you can see that line really levels out. And while smaller changes in the measured light level are going to create bigger perceived light level changes, it's difficult to get below that 1% mark. A lot of light fixtures today can put out thousands, maybe even tens of thousands of lumens. If you've got a light that goes down to 1%, that sounds great. But 1% of 10,000 lumens is still 100 lumens. That's still a very bright light. So if you're dealing in an application that requires really low light levels, the expectations that incandescents kind of brought or people's thought process around 1%, those aren't going to be matched with an LED that says 1%, but it's going into a restaurant or an architectural solution that requires even lower level than that. So here's some examples. You can see that if you're talking about a lobby or an atrium, even an open office area, working up in that kind of lighter blue shaded higher level, that's going to be perfectly fine. You're going to get a lot of energy savings by dimming that light down. You're going to see a good amount of changes in that light level. But if you're in a restaurant, a residence, an architectural hospitality solution, 1% is necessary, and in a lot of cases even lower than that. There's a lot of other issues people see with LEDs: flicker, shimmer, pop on. I'll explain. Pop on means that that driver that's driving that lamp needs a certain amount of voltage, or needs to be above a certain level in order to get that light to turn on. So as you ramp the dimmer up, the light's off, and then it reaches a certain threshold, the light pops on, and maybe you can dim down from there, but you don't get a nice smooth on. You get kind of a pop. Same thing on the dropout. You're dimming down, and then the light kind of suddenly turns off. Flicker's listed there twice. I don't know if I did that on purpose, but if I didn't, it should be there twice, because flicker is definitely the one that you see the most of. And then poor minimum light level kind of touches on what we talked about before in restaurants and architectural solutions. You really do need to get a good low level in those types of applications, and choosing the wrong LED control solution, not being compatible there, can really cause some issues. And again, these problems have been solved with existing light sources. Why accept them with LEDs? We're trained around really high quality lighting, so that's what people expect, and that's what we should be able to deliver. And a lot of times you can run into issues again with compatibility where that isn't delivered as clearly as and cleanly as it should be. So The driver is really the centerpiece here. The quality and the design of the driver determines the best possible dimming performance of the fixture. The driver's got a lot of hard work to do. The driver is taking your input power from the building, usually 120 or 277 volts AC. It's got to drop that voltage down. It's got to rectify that voltage. It's got to take a control signal in, whether that's changing voltage or whether that's a 0 to 10 or a digital signal. It's got to take whatever your control signal is in. It's got to convert that into a DC output that the LED engine can handle. It's got a lot to do. So choosing quality LED drivers that are compatible with your control systems is really essential to quality dimming, quality performance of the light fixture. And then compatibility between the dimmer and the driver determines how well they'll deliver the expected performance and lifetime together. The emergence of LED unlocks an enormous opportunity. So that we touched on this a little, but I want to go into more detail. Buildings are getting smarter, commercial buildings are getting smarter. And the question becomes, how do we integrate this smart technology in a way that we can get the most out? And lighting and the lighting control system serves as a really promising backbone for that technology. The reason for that is lighting is ubiquitous. It's all over the building. There's power readily available in every single light fixture. And as the lighting gets more intelligent and we begin communicating more with the lighting in a two-way fashion where we're talking to the lighting and the lighting's talking back to us, it provides us the opportunity to take more intelligence out of the lighting. Sensor arrays are getting less and less expensive. They're getting smaller and smaller, easier to install. We can learn more about our buildings and we can use our lighting control as a backbone to deliver that knowledge to a building management. And LEDs, again, I think are showing a really promising kind of way to deliver that. Lighting's ubiquitous, serve as the backbone. So let's talk about some load types. We're going to talk first about forward phase, reverse phase, kind of the original in terms of modern lighting control load types. 0 to 10 volt was probably the most common lighting control solution in the commercial environment currently, sometimes known as 4-wire dimming. We'll talk about digital controls, DALI. Talk about DMX. And then we'll talk about some wireless technologies as well. So let's dive into forward phase and reverse phase. So this is also known as 2-wire. Now, not included in this is the original 2-wire dimming. The original 2-wire dimming is rheostat dimming, resistive base dimming, and it's obsolete. You're not going to find that anywhere now. But the way to think about it, the old-fashioned dimmer, the old resistive dimmer, is we're just going to put a dimmer in line with this light bulb. We're going to burn up a lot of electricity in the dimmer, in the wall. We're going to turn it into heat. And all of that electricity that we burn up and turn into heat is electricity that's not going to go to the bulb. And therefore, the bulb will be dimmer. Works great, but it's not efficient at all. You're not saving energy by dimming. You're just burning it up in the bulb, or burning it up in the dimmer, I should say. So forward phase / reverse phase dimming here, it was really a breakthrough because it allows you to get that same 2-wire dimming while not using extra electricity. So we've got some visuals here of forward phase and reverse phase. And what you can see is happening is the alternating current sine wave, the AC sine wave shown here, is actually being cut. We're taking half that sine wave away. You can think of it as if an AC sine wave is 60 hertz, if it runs this cycle 60 times every single second, well, every time that sine wave crosses the middle point, crosses the 0 point, the light is actually off. There's 0 volts at that point. The light is turning off and on 120 times every second. It's too fast for the human eye to see, but the light is turning on, and with an incandescent, actually, it all kind of blends together anyway, but the light is actually turning off 120 times every second. So with forward phase, reverse phase dimming, we're just taking that time light's off and extending the amount of time that it's off. So in the case of the forward and reverse phase examples there. We've cut half of the sine wave out. The light is on half as often. It's still too fast for the human eye to see each individual on-off cycle. So it gets blended together as a 50% output, half bright output. The difference between forward and reverse is just which half we cut out. We're cutting out the front half, we're cutting out the back half. MLV, forward phase, magnetic low voltage, leading edge, these are all terms for the triac-based dimmer that was introduced to control magnetic loads, incandescent loads, loads that use a transformer, and it worked great. However, as things shifted more towards electronic-based dimming, a new type of dimmer, the ELV, came out and it flipped it around. That works better with a lot of LEDs and electronic versions. The distinction here, it's mostly academic. You in the real world don't need to know whether you're cutting out the front half or the back half of the sine wave, but the compatibility is very important. You want to look for these acronyms, MLV, ELV. You want to look for them on the control side. You want to look for them on the fixture side, and you want to make sure that compatibility is there. That your dimmer, if it's a magnetic low voltage dimmer, that you're finding a magnetic low voltage fixture to dim it with. The even trickier part about forward reverse phase compatibility is they can oftentimes appear to work for a period of time, and over time the incompatibility shows up. So you can put one in, it can dim the light, you can move on to your next project, and then the complaints start coming in. So this is one that I can tell you firsthand can really bite you if you don't pay attention or don't catch it early on. A lot of LEDs are marketing themselves as compatible with both MLV and ELV, both forward and reverse phase. A lot of dimmers now are saying that they adapt to the load. So the industry is trying to rectify this point of confusion, but it is important to remember that if you can find approved, tested, verified, compatible dimmers and loads, that's really a good way to go. But make sure this is something you're thinking about when you're looking at 2-wire lighting. 0 to 10. 0 to 10 has become the most common form of commercial lighting control. It doesn't have a lot of the compatibility forward phase, reverse phase issues, although there are some things to look out for that we'll talk about. This is just kind of a typical drawing of a 0 to 10 volt load. We call it 4 wires because the fixture is going to get a hot and a neutral, along with a DC positive and a DC negative. You can see in the drawing, there's actually a 5th ground wire. In kind of electrical lingo, you typically don't talk about the ground wire. It's there, but it's not counted. So that's why we get our 4 wire. In a 4 wire setup, the driver is going to get a constant hot or a switched hot. We'll talk about that, along with a neutral to drive it. Now, this is important because if you remember back to the 2 wire conversation, we were actually lowering the amount of voltage that we're sending to the driver. So modern drivers, they're really kind of mini computers. Imagine plugging your computer into the wall and then dimming it, reducing the voltage you're sending to your computer. Well, the electronics built into there are designed for 120 volts. That's what you're plugging into. It's difficult to design the electronics around functioning at a high level, even if you're getting half the voltage or 20% of the voltage. So 0 to 10 gives us an advantage by saying, no, we're going to give you 120 all the time or 277 all the time. You're always going to get that voltage. And instead of dimming that voltage, we're going to send a 10 volt DC signal on a separate pair of wires. And that will tell the fixture what level to go to. And it creates a higher level of dimming, and it also distributes the dimming out to each fixture. So if you're trying to dim an entire open office, for instance, you don't need one massive dimmer that can dim a whole conference room. You get one small 0 to 10 volt dimmer, and each driver can actually dim itself in a distributed fashion. So there's a lot of pros to 0 to 10. It's very standard. It's open protocol. Anybody, any manufacturer can make something that's 0 to 10, supported by almost every lighting manufacturer that's in the commercial space. The ubiquity of it means electricians are familiar with the technology. Most electricians that have been in the commercial industry know 0 to 10. They've installed 0 to 10. They're not figuring something new out. And as I mentioned, the dimming is localized in the driver, distributed out throughout the space. It's not centralized. You don't have to have a giant dimming rack in an electrical room to do a whole floor. You're taking that dimming and parceling it out fixture by fixture. Each fixture is dimming itself based on the command it's receiving. There are some drawbacks. It's polarity sensitive. One I can tell you about just very personally here is that gray wire, 0 to 10, for those of you who've been dealing with 0 to 10 for some time, know that the low voltage wires used to be purple and gray. And that gray wire up in the box, a 277 volt neutral is also a gray wire. And more than once, I've seen electricians accidentally wire the low voltage gray into the 277 volt neutral, which can be really dangerous, can damage equipment, can be really difficult to troubleshoot. And since then, the standard has actually been to change that gray in the 0 to 10 from gray to pink for that reason. Another drawback of 0 to 10 is that you do need to run a separate power and control switch leg for every zone. So I keep using the kind of example of an open office. And if you've got a large open office that it's all being controlled together at the same time, that's fine, that's not a problem. But if you want to break out your rooms into smaller control zones, you do need to break the wiring up piece by piece. Everything wired to a 0 to 10 volt switch leg is going to operate together. It's analog, meaning it's old-fashioned is too strong of a word, but it's limited in terms of the information that you can carry. You're running 2 wires to a fixture, and those 2 wires, because they're analog, the only piece of information they can carry is what light level you want the light to be at. It's not a digital 2-way form of communication. And then the last piece is it requires proper sync and source matching. I'm going to talk about that next, because sync and source is something that can be a little complicated and can definitely get you in trouble. 0 to 10 works in a way that's a little counterintuitive. You would imagine that the dimmer would send a voltage signal to the light to tell it what level to go to. Well, in 0 to 10, it's a little bit backwards most of the time. The fixture, the driver, is actually the source of the voltage. And it sends that 10 volts to the dimmer. The dimmer then syncs that voltage, it changes it, it manipulates it, and the driver, the light fixture, then sees that return voltage back and knows what to do. So a lot of times when you're troubleshooting, and this is more of a field situation, when you're troubleshooting, understanding which one is the source of the 10 volts, again, is a little counterintuitive. It comes from the fixture to the dimmer and then back to the fixture. You can find fixtures that are built as source fixtures. It's unusual, but more and more dimmers are actually being built to auto detect and change themselves to sync or source depending on what they're wired to. You'll see sometimes fixtures referred to as 1 to 10 instead of 0 to 10. Most fixtures, when you send them 0 volts, the purple and pink wires are only going to dim the light up and down. And if you take it all the way down to 0, if you go to the lowest possible signal, the light will settle down at its low end. It'll be on, but it'll be at low end. And then the control is responsible for incorporating a relay. You can see the relay drawn in there inside the dimmer. And when you want to turn that light off, you actually open the relay, you kill power to the fixture, and it turns off. Some fixtures do turn off at 0 volts, and you don't need the relay. So that's something that's kind of important to remember. If your fixture is a 0 to 10 volt that goes to low end, you do need a relay to ever turn that light off. Most control manufacturers build a relay into their 0 to 10 volt dimming and control components. Another issue on 0 to 10, this one's pretty important. If you go back to the very first slide, I said that safety is the most important thing that we do. Ensuring the lights are on when you need them is more important than anything else that we can do in this industry. Well, with 0 to 10 volt, because the light level is determined by a low voltage signal wire, 0 to 10 doesn't really fail safe to the on position. So if you're going to incorporate a UL 924 auto on safety type device. You do need to make sure that it's one that's compatible with 0 to 10. A 0 to 10 volt compatible UL 924 device is actually going to have the signal wire routed through it. You can see the violet there goes through that emergency device. It's actually going to not only ensure that the power is turned on to the light, but also that the 0 to 10 volt dimming signals are turned all the way onto the light as well. All right, digital. Digital is not nearly as common as 0 to 10, but it is still prevalent. DALI as a technology is much more common in Europe, but a lot of manufacturers have a DALI system in the US as well. I personally, as a programmer, am a big fan of DALI. It's a little more complicated, and again, it's not as ubiquitous as 0 to 10, but there's a lot of advantages to having a digital type system. When you have a digital system, every fixture is individually addressed. Every fixture has its own unique number, and you can control every fixture individually. DALI is an open source technology. It's managed by the DALI Alliance. They put the standards out. There's now a DALI 2, which is becoming the standard. So everybody can download the DALI details and build their own DALI. You can get it registered with DALI Alliance. Some manufacturers have proprietary versions of a DALI control, and DALI uses the same 4 wires as 0 to 10. You don't need a relay. All DALI fixtures turn themselves on and off. You don't need to kill power to the DALI fixture. In fact, you can't kill power to the DALI fixture, because if you do, it won't be online to listen to the command to turn itself back on if you kill power to it. So DALI stays energized all the time, but the fixture itself, the driver, will turn itself on and off. There's a lot of benefits to DALI. Digital addresses mean that one circuit can be divided into several control zones without pulling extra wire. In 0 to 10, we mentioned if you wanted to control separate lights separately, you needed to wire them together as a switch light. Well, in DALI, you can wire everything together and then break it out later however you want to control it. DALI's polarity insensitive. 0 to 10 is polarity sensitive. One of the major troubleshooting issues you're going to run into on a 0 to 10 volt application is, did the plus and minus get swapped somewhere? Well, DALI, that doesn't really matter. You can mix up the plus and minus all you want. DALI's still going to work. And just like 0 to 10, dimming is localized in the driver and distributed rather than centralized. There are definitely some drawbacks of DALI. It is less commonly used, so issues can arise during install. Because there are no wired switch legs, changing to another control technology can be difficult. This is a big one. If you wire a space with DALI in mind, you're not wiring switch legs. You're just powering everything, and you're doing your zoning later. Well, if you ever wanted to switch away or do something different, the wiring is not in place to support other control technologies. You're kind of stuck in a digital system, a digital wiring setup. So that can be an issue. And then last, manufacturer-specific versions can be proprietary, and that locks you a little bit and lets you limits the choices that you've got in terms of what you're going to install. Last, I'm going to mention DMX 512. DMX is known primarily as a theatrical lighting protocol. It is extremely fast, but it's also only one way. So a lot of what we've talked about before, a lot of lighting control, especially the digital, it's two-way. You get confirmations, hey, did you get that? Yeah, I got that. And there's a lot of kind of handshaking going on, knowing that everything's working. DMX is more like a shotgun blast. It's sending commands out all the time with really fast refresh rates. It says hundreds of channels. It's actually really easy to tell how many channels. It's 512 channels. You can support 512 channels in the DMX universe and constantly refresh those channels with what light level you want them to be at. If a device misses a command, it doesn't check or keep resending. It just keeps refreshing and says, okay, we'll get you the next time around. It's constantly blasting out all the commands. You go to this level, you go to this level, you go to this level, very, very quickly. That's great for theatrical for shows. You can see the picture here is the side of a building with a lot of different colors, and it's used in a lot of color tuning and color changing type lighting. We don't see it in generalized commercial lighting much, just because it doesn't integrate well with standard building control. The wiring is a little tricky, and it's a lot of features, high refresh like that, aren't really particularly useful to the general commercial application. See them used there much. All right, I'm going to talk a little about wireless. Wireless isn't a load type per se, but we're seeing more and more of it. So understanding how wireless works can be pretty important. Modern wireless technology, the range is getting better. The interference issues are getting less and less. The consistency is getting better. Wireless controllers can really reduce installation costs. They increase the flexibility of the space. They provide more control options. So there's a lot of really nice benefits with wireless. Building materials can hinder the range, and some customers are wary of the security and dependability issues. There's a few different wireless topologies. Point to point is simple. One device controls one thing. The two main ones you'll see out in the real world are star and mesh. Each one has some benefits. Star networks provide really reliable and precise communication. You've got one centralized node or receiver, hub, whatever term you want to use, and that one centralized device talks to multiple devices. If you want more than one hub or central point, that point A there in the middle of the star, you might wire it to another hub somewhere else in the building. So you've got wired communication between the nodes or the hubs, and then wireless within kind of their range. The big benefit here is the reliability and the precision, because one device is sending one command out to all of its little sub nodes, remote nodes. It knows they're all going to receive it, and they're all going to receive that command at the same time. So for instance, with wireless shades, if you want the shades speed to match, if you want the shades to be perfectly in sync, they need to receive that command to move at the same time. And a star network is more equipped to giving simultaneous commands at exactly the same point. Mesh networks, on the other hand, allow devices to repeat and retransmit and build kind of a larger network. So they're really scalable. They work better around walls or through thick building materials, because the mesh network can build its own pathways through the space. However, it does mean that different nodes are going to receive commands at different times, because something that goes straight from point A to point B, for instance, will receive it at one point in time, but if it has to go from A to B and then on to C and on to D, it might take longer for that command to get there, and you won't have the exact same precise type timing. And the more hops you get as well, you can imagine, the further out from the center point a mesh grows, the less reliable you get on the fringes. But they're very flexible in terms of kind of building larger spaces, covering larger. Using wireless technology, you can install fixture nodes without regard for existing wiring. This is a really great way to get around some of the earlier limitations we talked about with wiring. 0 to 10 volt, for instance, we're seeing a lot more 0 to 10 volt wireless nodes where you can use a 0 to 10 volt driver, a 0 to 10 volt fixture, but rather than pulling your low voltage wire all over the building, we can actually build a little 0 to 10 volt node directly into the fixture, build the relay directly into the fixture, and wirelessly pull that fixture. So it eliminates a lot of the negatives we talked about earlier for some of these other load types by building the wireless right in. Also sensors, occupant sensors, wall stations, daylight sensors. We can retrofit in, we can add them much easier, and you get a lot of benefits. A lot of times I hear people talk about the reliability of wireless, and well, it's not going to be as reliable as wired. And intuitively, I understand that. But in the real world, in a practical sense, wireless to me is a far more reliable method of communication than wired. Wired, sure, if you know that the wire's pulled well and installed well and wired well, wired's going to be more reliable. But in the real world, people go above ceilings. People troubleshoot things. Wires come loose. Wires get cut accidentally. Wires get miswired. Things get miswired or disconnected while there's some work done and then reconnected back in. Wireless, once you've ensured that the two devices are within range of each other, once you've paired them and placed them where they're going to live forever and ensured that they're within range, nobody's going to accidentally cut a wireless connection. Nobody can miswire a wireless connection. Wireless is it's just improving all the time, and it's become an extremely dependable, reliable form of communication that unlocks a lot of advantages that were previously not available. Just my kind of 2 cents on that. All right, last topic, color tuning. I think there's a more detailed color tuning conversation coming up. So this is just gonna be a really quick kind of touch on color tuning. This is something that I think a lot of us in the lighting industry are excited about. I know I'm excited about it. As we're putting more and more advanced technology into our lighting, we're unlocking more and more of the potential of that lighting. So we've always known how important color is. If you go to Home Depot and you get a color swatch from the paint section, they give you those little color, those lighting windows to kind of slide the color sample in to see how it's going to look in different types of lighting. We always have known how important it is. It's just been really difficult to unlock kind of dynamic color. We could pick what color we wanted, but to make that dynamic has been really, really difficult to unlock. So just as kind of a primer here, this is the black body curve. You may have seen this before, but essentially, if you burn something, a black body in this case, kind of the hypothetical perfect curve, it's going to shift through different colors, and those colors are shown here. I'll show you one that's a little more familiar to you. There's the Kelvin scale. So the important thing to remember about the Kelvin scale is that it feels a little backwards. We refer to things as being warmer, despite the fact that they've got a lower Kelvin. And the way to remember this is just to think about watching a fire burn. If you go back to the idea of burning on the black body scale, when a fire burns cooler, your color, the hotter the fire gets, the bluer, the whiter, and the bluer it gets. And this is kind of a visual representation of that. And with the modern LED technology that we're building into these fixtures, we have more and more the ability to dynamically shift through these color ranges rather than just statically picking one. So then the question becomes, well, why would we want to do that? What's the purpose of doing that? Well, earlier we talked about lighting that's on off. You're missing a whole world in between 0 and 100. You're missing a whole world that you can kind of edit and adjust between there. Well, in Kelvin, we're really unlocking the same thing. There's a world of colors, and they all have different purposes. People spend a lot of money on interior designers who spend a lot of money on artwork. People spend a lot of money on furnishings and finishings, carpets and wallpapers, and things like that. But the color of the light that we use to see those design choices heavily impacts the way we perceive them, and has an enormous impact on how well what we think about the space we're in, the mood of that space. This is a way to unlock that, and it's a way to really let a designer have that much more control over the space that they're designing. On top of that, we get into the idea of a circadian rhythm. The human body, humans over time have evolved to respond to these different colors in different ways, these different colors of the sun. So, and the research is still early, but we're hopeful that we'll see this idea of melatonin release and melatonin kind of starting and stopping, as well as your alertness levels starting and stopping, having that triggered through the color of the light you're surrounded by. So this is the circadian clock. There's a lot of research that's just starting on this. The Craig Montel lab at UC Santa Barbara has opened up. They're going to be studying this pretty substantially. We're still waiting for a lot more of the kind of peer-reviewed official research to come out on it. But there's a lot of evidence that this is going to be a really hopefully important way that we can like use lighting to make ourselves more productive over time. I've got just a different picture of the same idea here. You can just kind of see throughout the day. You can have your lighting help gradually introduce you into the workday with a warmer color as you get started. Then around kind of peak productivity time, much crisper, more alert, energetic light level in the space, and then help kind of relax you and get you kind of off of work mode as you head out with a warmer color at the end of the day. The hope is productivity will increase, whether that's in the workplace, whether that's in an educational facility, whether that's in senior living and memory care places that people are investing in this kind of thing. So again, research is still out, but we're hopeful and excited about the potential of circadian lighting moving forward. So let's just do some summary and takeaways here. Lighting is only good as the controls. Understanding controls is really important, and it's really complex. It's a wild, wild west still out there. Everyone is still circling and discovering the right ways to do things. We're all kind of unifying around standards. A lot of those are still being figured out. So making sure that the fixtures that you've chosen, the lighting you've chosen, the controls is key. Compatibility is key, and choosing the right solutions on the front end can save on enormous headaches later down the road. A lot of exciting technology. I mean, LED is just ubiquitous, kind of silly even to mention it. It is the standard. Wireless has a lot of potential moving forward. Color tuning, they're all at various stages of impacting the lighting environment, the lighting world that we find ourselves in.
Very good. So thank everyone for attending today. We hope this has been beneficial. So I'm going to turn it back over to Christine to keep in line with our 1 hour. So Christine, please take it away.
I hope you enjoy the rest of your day. Thanks, everyone. Bye.